So let us now continue with the details of the liquid bridge force models. First, let us look at the capillary force. This force is also present in case of no relative motion between the particles. What we do here as the first step is we calculate the pressure difference between the liquid in the bridge and the surrounding gas. We use the Young-Laplace equation, you see it here. Please be aware that this second contribution is here negative. And the reason is that this second principal radius, R2 here, is pointing to the outside. So this is actually decreasing the pressure. If you look at the quantities, you will see that this radius R2 is smaller than R1. So this term is larger. So the overall pressure in the bridge will be negative. That's very important. If you want to look into the details where you can find the equations for this principal radii R1 and R2, you can look it up in this publication of Lian et al. The next step is to then actually execute these calculations. And there are two options for that. Option A, step 2A, is using the so-called gauge method or the so-called toroidal approximation. And the toroidal approximation is nothing else as the assumption that this surface here of the liquid bridge is a circle. This is physically not consistent if you look into the Young-Laplace equation and the fact that there is no pressure difference within the liquid. However, it's a very often adopted assumption and it allows an analytical calculation of this R1 and R2. Again, please note that R1 and R2 are the principal radii of the free interface here and not the particle radii. If you have this, you could then calculate this delta P from this equation, and this is the contribution of the surface tension in this cross-section here, and you then end up essentially with this expression that is precise. However, again, R1 and R2 can only be found analytically if you assume this toroidal shape of the bridge. Again, this is the surface tension contribution just due to the surface tension force, and this is the pressure contribution. I told you before, delta P is negative from this equation because R2 is typically smaller than R1, meaning that this term is larger, giving an overall negative pressure in the bridge. The more often used approach to calculate the capillary force is this alternative B here. Here we do not adopt the toroidal assumption, but we perform a numerical solution for the liquid bridge shapes by directly evaluating the Young-Laplace equation. If you're interested in the details, I would like to recommend this excellent study from the year 2000. When you have solved for the shape, you get the R1 radius that we have seen on the previous slide. You get the delta P from the curvature of the surface, so you can evaluate the total force directly. And then the final step is just to approximate these numerical solutions with an analytical expression. Villet et al. Have done this in a very nice way. One of the equations that they have proposed is this one. And here we have the liquid bridge capillary force. 2 pi r is the radius of the particle. Here we have same shaped particles. Cosine theta here. Theta here is the contact angle. That's the angle between the tangential surface here and the free interface. This is known from literature depending on the liquid and the solid. Most important here is this expression here. You see that we have here a dimensionless distance d plus, and this d plus is defined as the distance. Here this is 2d, so d is actually the half distance between the two particles, divided by the square root of the liquid bridge volume V over R. Here you again see the definitions of these V star quantities and D star quantities. But the very important point here is you see that if the surface to surface distance d is 0, then this d plus is 0 no matter how large the liquid bridge volume is. If you then think about it, you will see that the liquid bridge force when the particles are in contact, so touching, is totally independent of the liquid bridge volume. And this is also what is the result out of many theoretical studies in the field. Again, I would like to stress that of course we have to consider a rupture distance. You see here a typical expression of this critical distance d crit star as a function of the bridge volume. So the bridge volume is the key ingredient for the rupture distance, but it does not affect the force at contact, so when the two particles are colliding, and essentially is, as you can see here, is stretching the range over which this force acts. Again, here we have the contact angle between the liquid and the particle surface. Let us now have a brief look at the so-called viscous forces. I told you before already that this is due to the squeezing flow of the liquid between the two particles. So if you imagine we have here liquid trapped between two particles and the particles are now moving, the liquid has to flow out of the bridge in case the particles are approaching each other, or vice versa, the liquid is sucked into the bridge if the particles are moving away from each other. For highly viscous liquids now, this effect of flow in the liquid bridge can have substantial consequences. For example, if you have a binder liquid with high viscosity, this can be of real big importance. People have worked out the effect of this squeezing flow and have come up with equations describing it. So here you see a typical one from Darabi et al. From 2009. You see the force scale is mu r squared, and then we have here this shear rate. So v rel over d, the distance, the half distance between the two particles, is a shear rate, right? This xv is a dimensionless correction factor accounting for the amount of liquid in the bridge. So you see here, if v is increasing here, this term is getting larger, this second term is getting smaller, so essentially V larger means a larger viscous force, how it should be, of course. It's also important that we specify a cutoff. You see here we divide by D, so we have to specify a minimal distance or half distance to be more precise, right? If you have particles that are soft and the viscosity is high, then it is also possible that the particles themselves deform under this extremely large viscous force, right? And then you will also find closures in literature, for example, Kentek and Davis, so-called elasto-hydrodynamic closure models for this viscous force. Here is this work from 2006. To finalize our discussion of liquid bridges now, I would like to close by showing you liquid bridges in action. So what I would like is to highlight how this liquid bridge affect now the force between a particle and a wall. For that, I have considered this test case here, relatively small particle impact velocity, very high surface tension. This is just for testing purposes, particle diameter 2 millimeters, and a fairly old but still okay liquid bridge closure for the capillary force from Mikami et al. If you now look at the force acting on the particle in the normal direction, you will see that after impact, and this is the impact time instant here, the force is strongly increasing. This is clearly the contact force as we have seen it already. Then the particle bounces back, it detaches from the wall, and now we have an attractive force here. That is due to the liquid bridges. And you see that this force is almost constant. You hardly see any change. There's only a very small change. And the reason for that is that the detachment of the particle from the wall is very small, and the amount of liquid bridge volume is so large that the change in the liquid bridge force is negligibly small. You then see that the particle is again moving towards the wall. There is a repulsion force. The contact force, and this is repeated a couple of times until the particle is then really sticking to the wall.